Okay, Bismillah Rahman Rahim. Assalamu alaikum. We are recording our first video lecture of this semester. Uh, Basically, because of orientation, section C missed one lecture on the first day of the semester. So I will be trying to make this lecture so that both sections can utilize this video lecture for their first online lecture. So one section might have studied these some quantities here in this lecture. So I will be trying to make this lecture uniform for both sections. Okay, starting from the name of the course, Digital Logic Design. The first slide you are seeing is basically defining what is digital and what is logic design. What is digital? Digital is concerned with the interconnection among digital components and modules. What the most common example of digital is a general purpose computer which we use. So how a digital computer and its components and its modules interconnect with each other, that quantity is called digital. And what is logic design? Logic design is basically the basic concepts and tools used to design the digital hardware consisting of logic circuits. We can say a mechanism which can perform arithmetic operations. Arithmetic operations, basic four arithmetic operations are addition, subtraction, multiplication, and division. So any mechanism which can perform these four arithmetic functions or and which can design or digital hardware is the logic design part of digital logic design. So the first slide is defining the course name. Okay, what are digital signals? Decimal values are difficult to represent in electrical systems. It is easier to use two voltage values than 10. So the first thing we can say that in our common life, we use decimal numbers as our main mathematical numbers. But in computers, we cannot represent, let's say, 0 to 9, 10 values in a digital computer. So digital signals consist of only two basic states, logic 0 and logic 1. Logic 0 is also called logic high or H or on, and logic 0 is also called logic low or simply L or off. So digital values are in binary format. Binary means two states, and we can also say that a light is, if a light is on, we can say it is logic high, or if it is off, we can say it is logic low. A good example of binary, a light can be either on and or off. So example of binaries is a light. Power switches have labels 1 for on and 0 for off. Uh, Often you have seen that in a power switch, it shows 1 for on and 0 for off in a similar understanding. Okay, this is some history of digital logic design. George Boole and Claude Shannon, these were the mathematicians which invented the uh, basically mathematical theories and logic and probabilities in 1854 and 1847. And Claude Shannon basically rediscovered Boole, and he applied the Boolean logic and Boolean algebra to digital circuitry. And after the World War II, the Arlington state machines were designed for the control of modern computer age. So this is some history of digital logic design. Motivation for the development of digital logic design, we can say microprocessors and microelectronics have revolutionized our world. We see cell phones, internet, and rapid advances in medicine, etc. The semiconductor industry has grown tremendously. So basically, the growth of semiconductor industry and basically miniaturization of digital circuits have revolutionized our uh, basically life. And microprocessors and microelectronics, these are the basic building tools of all the digital devices which we are using now. What are the objectives of this basically course? These are not the objectives of this lecture. Basically, these are the objectives of this course. We will see number systems, uses and conversions. Number system means binary numbers or decimal or octal numbers or hexadecimal numbers. These are the number systems. We will see their uses and conversions, basic building blocks of digital system, minimization, combinational and sequential logic. These are the two chapters or two sections of this course. And we will be studying design and analysis of both combinational and sequential logic circuits. And digital system, circuit analysis and design, state minimization, integrated circuits, and simulations. These are the basically parts of this course, or we can say CLOs, course learning outcomes of this course, or contents of this course. This is a textbook, Digital Design by M. Morris Mono and Michael D. Slatey, and Complementary Material Logic and Computer Design Fundamentals by M. Morris Mono and Charles Stein. I have already provided you the textbook and reference book. Okay. Number systems. Basically, we are starting our lecture here. The previous slides were just the introduction of the course. Now, what are the number systems? The decimal is the number system that we use in our common life, and binary is the number system which the computer use. And octal, what is octal? Octal is base 8, and this number system is used in groups of binary numbers. Binary shorthand, we can say octal is a shorthand of binary. It is used in digital displays or in modern times in conjunction with file permissions under Unix systems. Unix is a basically system which uses octal. Next slide basically explains why where octal was first used. Hexadecimal is a number system for base 16. It represents group of binary numbers, binary shorthand. Hex is a short of hexadecimal. Is primarily used in computing as most common form of expressing a human readable string representation of a byte group of 8 bits. So basically, hexadecimal numbers will be used in to represent a byte, or these are also used in some computing quantities. Okay, this is some overview design of computers. It all starts with numbers. When we have to design a computer, it all starts with numbers. Means we break up our problem into numbers, then we design building circuits, then we design or digital circuit or digital computer, its components by digital mathematical models, then building computing machines, digital systems. What are digital systems? Understanding the decimal numbers, binary and octal numbers, and conversion between these numbers. These are the overview of this next few slides. Basically, we will study what is a binary number and what is a octal number, and how we convert between these two bases. Okay, first we differentiate between an analog and a digital signal. What is an analog signal and what is a digital signal? In short, we can say an analog signal is a continuous signal whose values rapidly change uh, from one value to other value with the passage of time, whereas a digital signal has either logic 1 or logic 0. We can represent logic 1 by plus 5 volt, or logic 0 with minus 5 volt, or we can represent logic 0 with 0 volt. So a digital signal has two discrete values, 1 or 0, whereas the analog signal has a continuous variation in its values. Here he has given some example. Water can be flowing or not flowing from a faucet. Faucet is basically a tap. So there are two on states. A tap can either be on or it can be off. In analog, we can say how much water is flowing from the faucet, how much water is coming out of tap, which will be a variable quantity. So advantages of digital. What are the advantages of digital? Next slide is basically telling the advantages of digital. In digital quantities, we can detect or correct an error very easily, basically in what is the error in a digital signal. A bit 0 can convert change into 1, or a bit 1 can change into 0. So there are these two possible errors which can occur in a digital circuit. So in analog signal, in basically error is not that simple. Basically in analog signal there is a wide variation of errors which can happen in an analog circuit. So this is one advantage of a digital circuit, that error can be detected and corrected very easily. Miniaturization of circuit. Because of integrated circuits, we can implement a very complex digital circuit into a very small chip. You might have seen a micro SD card, or 1 terabyte micro SD card can be a very short, very small card which can store a huge amount of data of size 1 terabyte. So miniaturization of circuits is the advantage of digital circuits. Programmability is another advantage of digital. We can program the digital computers, and computers can follow that program. So digital circuits are programmable, where analog signals circuits are not programmable. Okay, two discrete values used in digital system. We already tell electric signals use voltage and current. We can use voltage and current to represent a logic high or logic zero in a digital circuit. Okay, here he has shown some, basically what this slide is telling you. This slide is telling you that from 2 volts to 5 volt we can set as a logic high, and from, we can say, 0 to, let's say, zero point 0.7 volt, we can fix it at logic low. Acha, logic high or logic low, or we can say logic 1 and logic 0. Acha, first question is, why are their voltage ranges instead of exact voltages? Why have we used from 2 volt to 5 volt as logic high? Why haven't we used just a single value of voltage, let's say 5 volt as logic high and 0 volt for logic 0? So answer to this question is that when we design a digital circuit, or a circuit which provide us with these logic circuits, so there is some variation or noise, or we can say fluctuations in the circuit. So if we fix that 5 volt will mean that it is logic high, and anything other than 5 volt, anything less than 5 volt is not logic high, then the logic uh, high or logic 1 will not be a we can say stable state. So in order to make it a stable state, we make logic high, or we define logic high as from 2 volt to 5 volt as logic high. So we allow the basically our digital circuit some compensation or some tolerance in its high voltage state. Similarly, in logic low state or logic zero state, we can say from 0 volt to zero point 0.7, zero point 0.8 volt, we can define this range as logic 0. So uh, there is some tolerance range in logic 0 as well. So we are not defining exact 0 as logic low. We are giving it some tolerance of variation which are present in a digital circuit, or of such circuit which is providing us these logic circuits. So possible values 1 and 0, we already defined that 1 and 0, on and off, true, false, high, low, hash tails, or black and white. These are the possible values of a binary values. Here is a table between analog and digital. Basically, he has, if you see the leftmost column, the technology comparison between analog and digital, uses of analog and digital, signals, representation, memory units, applications, data transmission, results, storage capacity, process, response to noise, and waves. These parameters have been discussed for both analog and digital. We can say, for example, memory unit. Analog does not require a memory unit, whereas digital uh, technology requires a medical memory unit. Or there are other data transmission, not high quality data transmission, whereas in digital there is very high quality of data transmission. In result, analog result is not very accurate, whereas digital circuit is very accurate. So response to noise more likely to get effective, reducing accuracy. So analog circuits are very prone to noise, whereas discrete digital circuits less affected since noise response are analog in nature. So in digital circuits, the noise is very low. So these are a basic comparison between analog and digital circuits. Okay, next, uh, when we design a digital computer, what we design basically discrete amount of data, 26 letters of alphabets, 10 decimal digits. These are the quantities which we design in a computer. Large quantities can be built from discrete values, words made of letters or decimal digits. Computer can operate binary values. We already defined that. Okay, easy to represent binary values electrically. We already defined that. We can use voltages to represent binary values. Understanding decimal numbers, a decimal number will have digits from 0 to 9, 0 to 9, 10 digits. And if we, how can we break up a decimal number? 8,653 can be broken up into 8 into 10 raised to the power 3, 8,600 and 500, 5 tens and 3 units. We can say 8 into 10 raised to the power 3, 8, most significant bit 8 into next, there are 3 digits, so 10 raised to the power 3, and next digit is 6, 6 into 10 raised to the power 2 plus 5 into 10 raised to the power 1 plus 3 into 10 raised to the power 0. So if we add all these, we will get the decimal 8,653. And similarly, a fraction number can also be broken up into similar method, 9 into 10 raised to the power 4. Up to 4, we can repeat the above process, and after the decimal, up to 4 into 10 raised to the power 0, up to here we have repeated the above process, and after the decimal we have 3 into 10 raised to the power minus 1 and 5 into 10 raised to the power minus 2. So if we add all of these, we will get 97654.35, this number, which is a fraction or decimal number. In formal notation, we can say 97654.35, this is a decimal number or base 10 number. Why we use 10 digits anyway? Why we use 10 digits? Because decimal number consists of 10 digits, and in our normal life all the numbers we use are decimal numbers. What is a octal number? Octal numbers are made of octal digits which are from 0 to 7. 0, 1, 2, 3, 4, 5, 6, 7. These are the octal digits. And how can we break up a octal number? 4, 5, 3, 6, base 8 octal number. In a similar method like decimal numbers, we can break a octal number like 4 most significant bit into 8 raised to the power 3. There are 3 digits after 4, so 8 raised to the power 3 plus 5 into 8 raised to the power 2 plus 3 into 8 raised to the power 1 plus 6 into 8 raised to the power 0. So if we add all of these and evaluate their products, we will get 1362, which is a decimal equivalent of this octal number. So here we are basically breaking up a octal number and evaluating its decimal equivalent. What about fractions? Fractions are similar to last slide, basically what we done in last slides. Here only difference is the mm, base will is 8. In last slide there was base 10, and in this slide there is base 8. 4 into 8 raised to 6 into 8 raised to power 1 plus 5 into 8 raised to power 0. After the decimal, 2 into 8 raised to power minus 1 and 7 into 8 raised to power minus 2. Okay. Octal number don't use digits 8 or 9 because when we divide by 8, the remainder cannot be 8 or 9. Who would use octal number anyway? Who will use octal number anyway? This slide, next slide is basically octal number became widely used in computing when systems such as UNIVAC 1050 and PDP-8, ICL 1900, and IBM mainframes employed 6-bit, 12-bit, 24-bit, and 36-bit words. So these word sizes were different from the usual sizes. So octal was an ideal abbreviation of binary for these machines because their word size is divisible by 3. Each octal digit represents the 3 binary digits. We will see that 3 binary digits represents a octal digit. So this is the basic answer to this question: who would use an octal number anyway? This is how octal numbers came into use. Understanding binary numbers. Binary numbers, we already defined that why binary numbers are called bits. Binary, B for binary, and digits, ITs. We, that's why it is called bits. Binary digit can have a bit 0 or bit 1. And how we can break up a binary number. For example, 1011 base 2, this is a binary number. We can break it up like the previous method: 1 into 2 raised to power 3 plus 0 into 2 raised to power 2 plus 1 into 2 raised to power 1 plus 1 into 2 raised to power 0. And if we evaluate all these four products, this is 8, this is 0, this is 2, and this is 1. 8 plus 2 plus 1 is 11, which is the decimal equivalent of this binary number. Similarly, about these fractions, 110.10, repeat the same process. After the decimal, you uh, do the same process: 1 into 2 raised to power minus 1, 0 into 2 raised to power minus 2, and you get this number. Group of 8 bits are called byte. 8 bits, group of 8 bits is called a byte, and group of 4 bits is called a nibble. So half a byte is called a nibble. These are some definitions. Why we use binary numbers? Easy to represent 0 and 1 using electrical values, possible to tolerate noise, easy to transmit data in form of 0 and 1s, and easy to build binary circuits. For example, an AND gate can be designed for these two values, binary numbers 1 and 0. We will define AND gate in our coming lectures. AND gate basically gives you a logic 1 output only if both of its inputs are 1. If any of its inputs is 0 or both the inputs are 0, it gives you logic 0 at the output. So binary numbers can be used in designing the binary circuits. This is the same thing which we have defined below, that this range is for logic 1 and this range is for logic 0. We already defined this, why we use a range and why we don't use a exact value for this logic high or logic low. Okay, binary, in binary there are only zeros and ones. These numbers are called base 2. For example, 0, this is example. Binary to decimal, base 2 and base 10. Okay, this is basically, we can say that in base 10 the 0 can be represented by, in base 2 by 3 bits, 000. In base, the decimal 1 can be represented by 001. Next, decimal 2 can be represented by 010 in base 2. This conversion can be done by dividing a number with 2 repeatedly. So next, 011 is equivalent to decimal 3, and 100 is decimal 4, and 101 is decimal 5, and 110 is decimal 6, and 111 is decimal 7. So base 2 and base 10, these are the comparison of, or we can say equivalence of, base 2 and base 10. 7 in decimal can be represented by 111 is base 2. We count in base 10 0 to 9. Binary has base 2, Each digit is one of two numbers, 0 or 1. We already told you that binary has two values. Each digit is called a bit. 8 binary bits make a byte. We already defined it in last slide. All 256 possible values of a byte can be represented using two digits in hexadecimal notations. This last fact we will discuss in our future lectures, that 256 possible values of a byte can be represented using two digits in a hexadecimal notation. How we can do this, we can define it in our future lectures. Finally, as a voltage are used to represent logic values. We already told you that a voltage present called VCC or VDD is equal to 1. If a voltage is present and you connect the switch to that voltage, it will be logic 1. 0 volts or ground will be logic 0. A simple switch can provide you logic high or logic low. Here is a simple switch used to provide logic value. Here you have a switch which can connect at VCC or ground. If it is connected at VCC, it is logic 1, and if it is connected at ground, it is logic 0. There are other ways to connect to a switch. Other than this diagram, we can connect a switch in other ways as well. Bit is a single binary digit. Byte is 8 binary digit. Already defined that 8 bits are called a byte. This is one single digit is called a bit, and base 2 is the radii. Okay, conversion between number bases. A decimal number can be converted into base 2, or base 2 can be converted into decimal. Similarly, binary can be converted into base 8, or base 8 can be converted into base 2. Or similarly, hexa number can be converted into base 2, or hexa or base 2 can be converted into hexa. So we will learn how to convert these interconversion between number systems in a coming lecture. This is a table: decimal, binary, octal, hexa, their bases, their symbols, and humans use decimal. Humans use decimal, and computers use binary numbers. So humans use decimal numbers, and computers use binary numbers. This is a table which is summarizing all the number systems. These are the possibilities. We already defined this in a table: decimal, binary, octal, and hexa. They all can be interconverted from one base to another. Okay. Okay, this is the process of converting base 10 number into a binary number. You probably know this process. If we have 13 decimal number, we repeatedly divide it by 2, and then the remainders are in reverse process, are basically collected, and 1101 is the uh, decimal, basically binary equivalent number. So 13 was the decimal number. We divided 13 by 2. We got 6 as remainder, 6 as the quotient, and 0 as the remainder, 1 as the remainder. And then we repeatedly divided the quotient. We divided 6 by 3. 3 is the quotient, and 0 is the remainder. Then we divided 3 by 2. 1 is the quotient, and 1 is the remainder. And we collected the basically uh, remainder, and in reverse order we arrange them, and 1101 is the binary equivalent of this decimal 13. We can repeat the same process for any base. For octal, we can repeatedly divide it with 8, and for any general number, we can we can you excuse me for 1 second? Okay. uh, This is a process of converting a decimal number into a binary number. And this same process can be repeated for any base. And remember that you always divide a decimal number with a base in which you want to go. You cannot divide a big octal number with a repeated base. You always divide a decimal number with a base. Okay, convert a fraction from decimal to another base. Here is a process of, let's say we have a 0.625 decimal number and we want to convert it into a binary number. So what we will do, multiply the decimal number by 2. The integer is the highest order digit, and repeat the first two steps until the fraction becomes 0. So 0.625 into 2 becomes 1.25. 1 is the integer, 0.25 is the fraction. Then multiply 0.25 by 2, it becomes 0.050. 0 is the integer, zero point 0.5 is the fraction. Multiply zero point 0.5 by 2, integer is 1 and fraction becomes 0. So we repeat it until the fraction becomes 0, and then in the straight order, 101.101 is the decimal binary equivalent of this decimal 0.625. So we have converted the fractional number into a binary equivalent. So this is the process of converging a decimal fraction into a binary number. Here is the growth of binary numbers n and 2 raised to power n. For example, 0, 2 raised to power, if n is 0, if n is 0 means 0 can be, there can be only one value 0. Now, if n is equal to 1, 2 raised to power 1 means there are two possible values of a bit. One bit can have two possible values, which is 1 and 0. Two bits can have four possible values, 0, 0, 0, 1, 1, 0, 1, 1, four values. In a similar method, we can say 3 bits can have 8 possible values, 4 bits can have 16, and you can go growth of binary number. And the most common units which you use is 2 raised to power 20 is 1 mega, 2 raised to power 30 is 1 giga, and 2 raised to power 40 is 1 tera. These are the growth of binary numbers. Binary addition is similar to decimal addition. You add 1 with 1, 1 plus 1 is 2. 2 in binary is 1 0. So you write 0 here and 1 is carry. And then you add again 1 plus 1 is 2. 2 is 1 0 in binary. So you write 0 here and 1 is carry. 1 plus 1 plus 1 is 3. 3 is double 1 in binary. Write 1 here and 1 here. 1 is carried. So you keep on adding these numbers and carries. You get that sum of these two binary numbers. It is similar to decimal addition. The only difference is the sum should be in binary. 1 plus 1, you cannot write 2 here. You write it in binary 2, which is 1 0. You write 0 here and 1 here, and keep on adding the carries and the numbers, and you get the sum of two binary numbers. Similarly, the subtraction is similar to that or in uh, decimal numbers, but only difference is 1 minus 1 is 0. Wait, 1 minus 1 is 0, and you cannot subtract 1 from 0. So what we will do, we will take a carry from here, and it will become 1 0 means it will become 2. 2 minus 1 is 1, and this becomes 0. Then again we take a carry from here, 1 0 becomes 2. 2 minus 1 is 1. This again becomes 0. 0 minus 0 is 0. Then again we cannot take subtract 1 from 0, so we take a borrow here. This becomes 2. Then take a borrow here, 2. 2 minus 1 is 1. And here basically it was when we took a borrow from here to here, this become 2, and then we took the borrow from here. So this one will be 1. 1 minus 0 is 1, and this is already 0 because we have already taken it borrow. So this is the difference of these two binary numbers. It is similar to decimal number, but only difference is that when you take a borrow, you deal with binary quantities, not decimal quantities. Okay, multiplication is very simple. 0 multiplied this number is all zeros. 1 multiplied by this number is this number. Exact 10111 will be repeated here. You leave one bit here. Then 0 multiplied by this number, all zeros. Then 1 multiplied by this number, again this number. So you add all of these, just like in decimal multiplication. So uh, this is the multiplication of a binary. This is much simpler, similar to decimal numbers, but it is much simpler. Convert an integer from decimal to octal. Decimal to octal, repeated division by 8. Just like previously, we repeatedly divided by 2 and we got binary number. Similarly, we can do it for octal number. Repeatedly divide by 8, you have a quotient, you have a remainder, and then you arrange them in reverse order. 257 base 8 is the octal number of 175 decimal number. This is similar to converting a binary number from a decimal number. The only difference is here we repeatedly divide by 8 instead of 2. And again, converting a fraction into, basically what we are doing here, our decimal fraction is converted into octal. 0.3125 multiplied by 8, the integer is 2 and fraction is 5. Then basically it becomes 0.3125 multiplied by 8 is 2.5. So 2 is the integer and fraction is 5. Then we multiply 0.5 into multiply by 8. It becomes 4.0. So we repeat that process until the fraction becomes 0. So 2 and 4 are the integers. So we arrange them in straight order. 0.24 octal is the uh, base 8 equivalent of 0.3125 decimal number. This is similar to last method which we use for binary. Summary: binary numbers are made of binary digits. Binary and octal numbers, conversion between number systems, addition, subtraction, and multiplication of binary. So this is what we have done in this lecture. So we can discuss this lecture in detail in our live session online on Thursday for both sections, section B and C. Okay, Allah Hafiz. Thank you.